$5 billion and 10 million cubic meters define one river's ultimate fate as a massive wall halts the Nile's force. But first, turbulent water crashes through giant steel gates while extreme hydraulic pressure tests reinforced concrete. Beneath it, dynamite tears through dense bedrock as shifting formations threaten structural stability. And 2,000 kilometers downstream, Cairo sleeps while 100 million citizens depend on this river. Even the construction itself becomes a battle, as 45-degree heat stresses concrete monoliths while internal cooling prevents cracking. Inside, massive turbines spin under extreme pressure, where imbalance threatens heavy steel housings. Then 74 billion cubic meters begin pressing against the dam, loading the granite below. But before engineers could control that immense reservoir, they first had to survive seasonal floods tearing through the gorge and threatening their early diversion barriers. Before trapping the river, engineers first build vital lifelines, cutting more than 100 kilometers of heavy access roads through remote granite terrain. But 80-kilometer-per-hour Haboob sandstorms strike without warning, reducing visibility around heavy machinery working beside steep valley cliffs. Caterpillar 777 dump trucks then haul 70-ton boulders continuously, keeping raw construction materials moving across the remote border wilderness around the clock. To reroute the powerful Blue Nile, crews excavate a massive artificial bypass channel through nearly 5 million cubic meters of dense bedrock. Komatsu PC-800 excavators tear into stubborn ancient granite, forcing heavy bucket teeth and hydraulic systems to work under extreme mechanical pressure. Precision drilling rigs prepare carefully spaced blast patterns, allowing controlled explosive charges to fracture thousands of tons of rock with each detonation. Sequential detonators then fire along the channel centerline, shattering stubborn granite without damaging foundation zones needed for long-term structural stability. Upstream and downstream, crews build massive rock-filled cofferdams to isolate the future dam footprint from the Nile's ferocious seasonal flow. Heavy piling rigs drive interlocking steel sheet piles through gravel layers, creating watertight barriers around the deep foundation excavation. But rising seasonal floods threaten to breach those temporary defenses, pushing machinery and construction operations toward their absolute limits. High-capacity submersible pumps continuously remove trapped river water, discharging hundreds of thousands of liters back into the artificial bypass channel. Then explosive charges remove the final temporary plug, allowing the mighty Blue Nile to surge into its new man-made course for the first time. With the river diverted, its ancient natural path suddenly lies dry, exposing layers of silt deposited across the riverbed over millions of years. Engineers inspect the exposed alluvial deposits and soft clay layers, preparing to excavate downward until pristine solid granite is finally reached. A temporary steel truss bridge spans the roaring bypass channel, carrying heavy machinery and structural components continuously into the main construction zone. Massive batching plants rise along the dry canyon walls while conveyor systems stretch for kilometers to support the enormous concrete operation ahead. Yet unpredictable upstream flash floods can still send powerful surges downstream, forcing cofferdam instruments to monitor dangerous hydrostatic pressure increases continuously. Erosion also attacks temporary diversion walls, so high-pressure shotcrete systems apply protective mortar layers across vulnerable exposed banks. Overland conveyor belts undergo continuous stress testing as mechanical rollers transport huge quantities of crushed aggregate across the difficult gorge terrain. Fuel tanker convoys navigate steep mountain switchbacks every day, delivering thousands of liters of diesel needed to keep remote construction operating non-stop. At last, the diversion system stands complete, the rock walls remain stable, and the Blue Nile flows safely around the exposed dam foundation. But beneath that newly dry riverbed, hidden subterranean fault lines now threaten to undermine the entire structure before the main dam can rise. Exposed foundation granite reveals hidden weaknesses as geologists discover deep fault lines directly beneath the main dam footprint. Heavy epirock rigs drill hundreds of precision holes, boring 50 meters into solid crystalline rock. But underground aquifers create another threat, forcing high-pressure water through fractured rock and destabilizing deep excavations. Controlled smooth wall blasting protects the surrounding foundation from microfractures, while breaking only targeted rock zones. Komatsu PC-800 excavators then clear thousands of tons of blasted granite as hydraulic breakers reduce massive boulders for transport. To stop subterranean seepage, giant hydromill cutters excavate bentonite cutoff walls 60 meters deep. Dense bentonite slurry continuously supports these trenches with hydrostatic pressure, preventing their walls from collapsing. High-pressure grout pumps then force sealing mixtures into microscopic rock fissures at pressures reaching 100 bar. Deep underground piezometers and geotechnical instruments continuously monitor rock deformation and changing pore water pressure. Hundreds of high-strength steel anchors secure unstable granite blocks into stronger underlying mountain strata. Cranes then lower massive reinforcement cages into slurry trenches before tremi-concrete permanently replaces the bentonite. High-pressure water jets strip away weathered surface rock until fresh crystalline granite is exposed for direct concrete bonding. Geologists systematically map the exposed foundation, while ultrasonic testing searches for remaining voids inside the structural rock. Compressed air systems then flush crushed stone and moisture from deep drill holes before final grout consolidation. Beneath the foundation, engineers carve a subterranean curtain gallery through solid granite to provide permanent access for grout maintenance. Specialized rigs drill inclined holes from this gallery, as high-pressure cement slurry creates an impermeable underground grout curtain. Before concrete placement begins, temperature sensors are embedded throughout the foundation to monitor dangerous thermal expansion during curing. Massive dental concrete pores fill irregular granite depressions, creating smooth level pads for the coming RCC lifts. Heavy vacuum systems remove the final dust particles, leaving a clean rock interface capable of achieving maximum concrete bonding strength. Final core drilling confirms no remaining water flow through the treated foundation, proving the subterranean granite shield is sealed. Engineers can finally approve the deep foundation, clearing the way for the largest continuous concrete operation in African history. But one threat remains. 45-degree heat could flash cure 10 million cubic meters of concrete before the dam can rise. 10 million cubic meters of roller compacted concrete begin to flow as continuous operations run around the clock beneath the scorching desert sun. But 45-degree heat threatens rapid curing, as evaporating water creates dangerous thermal stress throughout the massive concrete lifts. To control temperature, automated batching plants produce ice-cooled mixes, using flake ice to lower placement temperatures below 20 degrees. Multi-kilometer conveyor systems then transport thousands of tons of dry zero-slump concrete directly toward active placement zones. Rotary spreaders distribute the mix while heavy bulldozers grade each 30-centimeter lift with precise elevation control. Ham vibratory rollers follow immediately, using high-frequency compaction to lock aggregate particles into a dense, nearly void-free mass. The danger is microscopic because even a tiny crack under immense hydrostatic pressure could drive enormous water flow through the dam body. Miles of HDPE cooling pipes are therefore embedded through fresh lifts, circulating cold water to extract heat generated during cement hydration. High-capacity industrial chillers operate continuously as internal sensors verify falling temperatures before thermal expansion can strain adjacent blocks. Once each lift cures, high-pressure air and water remove weak surface material, exposing aggregate needed to bond with the next layer. Along the upstream face, grout-enriched RCC is carefully consolidated against formwork to create a dense, watertight outer barrier. Self-climbing hydraulic formwork then rises continuously along the growing monolith as newly placed concrete cures below. Quality control teams extract cured cores, where hydraulic compression tests verify that each section reaches its required 90-day strength. Yet sandstorms can coat prepared surfaces with fine dust, forcing powerful vacuum sweepers to clean every joint before construction continues. Bedding mortar is then spread across the cleaned interface, strengthening the bond and reducing shear risk between horizontal lifts. As layer follows layer, 10 million cubic meters of concrete form a structure whose shear mass becomes almost impossible to comprehend. Flexible copper water stops are embedded through expansion joints, allowing neighboring blocks to move independently while maintaining a watertight barrier. Deep inside the dam, suspended plumb lines and laser sensors continuously detect tiny structural movements caused by changing thermal conditions. Under enormous floodlights, night shifts keep trucks, spreaders, and rollers moving as the concrete wall climbs toward 145 meters. Eventually, the main dam reaches its final crest elevation after millions of continuous work hours. The colossal RCC monolith now stands fully cured, allowing engineers to shift their attention from concrete construction to hydroelectric machinery. But the next operation leaves almost no margin for error, as 35-ton turbine runners must be lowered into confined powerhouse shafts deep inside the structure. Inside the cavernous underground powerhouse, installation begins as engineers prepare 16 massive Francis turbine units designed to produce more than 5,000 megawatts. Heavy multi-axle SPMTs transport 35-ton stainless steel runners through narrow access tunnels with only inches of clearance. Inside the powerhouse, a 1,200-ton overhead crane lifts each runner above its turbine pit as high-tensile cables carry the enormous suspended load. Sub-millimeter alignment is critical under 140 meters of hydrostatic head because even microscopic errors could destroy heavy bearing assemblies. Massive spiral scroll cases are assembled around the turbine pits, distributing incoming high-pressure water uniformly around each runner. Hydraulic torque systems then pretension enormous flange bolts, creating sealed connections capable of resisting extreme water pressure. During dry testing, vibration sensors confirm each Francis runner is balanced within a fraction of a millimeter. 8-meter diameter steel penstocks descend toward the powerhouse, built to withstand the crushing hydraulic forces of the reservoir above. Automated orbital welding systems seal each penstock joint, while ultrasonic testing searches every seam for hidden internal defects. Heavy gantry cranes then lower 100-ton intake gates into vertical guide slots, where thick seals form watertight barriers. Inside each generator, massive rotor assemblies descend precisely into surrounding stators, leaving only millimeters of electromagnetic clearance. Outside the powerhouse, high-voltage step-up transformers prepare to transmit generated electricity through 500 kilovolt infrastructure. Hydraulic servo actuators control the wicket gates, continuously adjusting water flow through each Francis runner. Below the turbines, smooth steel draft tubes are encased in reinforced concrete to control discharge and minimize energy-robbing turbulence. Massive thrust bearings support thousands of tons of rotating vertical machinery, while synthetic oil prevents direct metal contact at operating speed. Governor systems undergo emergency simulations, rapidly closing hydraulic controls to prevent a runaway turbine during abnormal conditions. Overhead cranes position 20-meter generator shafts while precision lasers verify absolute vertical alignment above the lower bearings. At the upstream intakes, automated rake systems clear floating debris from massive trash racks before it can reach the turbine blades. Then the first wet test begins, sending high-pressure water through a penstock and into an early turbine unit for the first time. The giant generator accelerates towards synchronized grid speed as mechanical alignment and electrical systems reach generation readiness. With all 16 Francis units installed and verified, the powerhouse stands ready to harness the immense reservoir behind the dam. But activating that power means holding back 74 billion cubic meters of water, transforming the engineering challenge into something far larger than machinery alone. Heavy diversion gates descend, halting the Blue Nile as 74 billion cubic meters begin filling the vast reservoir. Upstream levels rise across hundreds of square kilometers, transforming narrow valleys into an enormous inland lake. Downstream monitoring stations detect falling discharge, raising concern over changing Nile flows reaching Sudan and Egypt. Automated control systems monitor incoming floods and operate 100-ton radial gates whenever additional discharge is required. Water accelerates down the spillway at nearly 40 meters per second, creating enough energy to threaten destructive cavitation. Aerator steps inject air beneath the flow, protecting concrete surfaces from damaging pressure effects. Massive flip buckets then launch torrents away from the dam, dissipating energy downstream. As the reservoir grows heavier, tilt sensors and piezometers monitor structural movement and foundation pressure. A 5-kilometer rock-fill saddle dam seals surrounding mountain gaps and limits leakage through side ridges. Satellite telemetry tracks reservoir elevation and filling rates across the Nile system. During dry seasons, low-level outlets maintain controlled downstream flows. In Sudan, farmers monitor river levels as regulated discharge changes seasonal conditions. Beneath the reservoir, acoustic sensors detect seismic tremors caused by regional tectonic movement. When exceptional rainfall raises water levels, excess flow passes safely across ungated crest spillways. Powerful torrents strike deep plunge pools, dissipating energy without undermining the dam foundation. Engineers precisely adjust radial gates, balancing reservoir head against downstream flow requirements. Continuous water balance calculations prevent rapid drawdown and dangerous pressure changes across the upstream wall. Meteorological stations monitor evaporation and atmospheric conditions above the reservoir. Sediment systems track accumulating silt, while flushing outlets move sediment-rich water downstream. International observers inspect release infrastructure and monitor downstream flow data. Eventually, 74 billion cubic meters reach the target reservoir volume, storing immense hydraulic energy behind the dam. But controlling the river is only part of the challenge, because more than 5,000 megawatts must now cross vast stretches of rugged wilderness. 5,000 megawatts surge through 500 kilovolt gas-insulated switchgear as circuit breakers route electricity into regional grids. Sudden frequency instability threatens the network, forcing automated compensation systems to stabilize reactive power within milliseconds. Thousands of high-voltage towers carry massive conductor bundles across rugged terrain and mountain ranges. Across rural communities, reliable electricity brings light to homes that previously lacked dependable power. High-voltage interconnectors energize industrial centers, allowing automated factories to operate on renewable hydroelectric power. Downstream, regulated river flows support agriculture through more stable irrigation conditions. Electric pumping stations replace diesel generators, moving river water through canals toward newly cultivated farmland. Cross-border transmission lines export hydroelectricity toward neighboring countries, expanding regional energy trade. Modern dispatch centers continuously balance generation and electricity flows across interconnected grids. Now fully operational, the $5 billion engineering project combines immense concrete structures, hydraulic machinery, and electrical infrastructure. 10 million cubic meters of concrete hold back the Nile, transforming its immense hydraulic force into controlled energy. The river continues downstream, while the colossal dam stands behind it as one of Africa's most ambitious engineering achievements.
NextGen Machine Works, building the impossible. Subscribe to join the future.